It's on. So if anybody would like to give a talk, is it a 15-minute talk, a short talk, please talk to Rogerio over there. In this right, so there's going to be a talk today during. Okay, we have 2 talks today already. That was very productive, very fast. Okay, 4 talks or some other time, just please see Rogerio. Then all of you received an email with the dinner tomorrow. So just in case if you have any doubt, the organizers. And so now these people will not have dinner for them because they are late. So so now we're going to go to the second lecture by Nicolás Bernal on his dark materials.
And the soccer?
No, no soccer. Oh, okay, so you should make him happy today while he can, because tonight he's going to be very sad after the game. So.
The lecture may be cancelled tomorrow. Okay, so super loud, no? It's okay? Okay. So, okay, the idea is to continue the dark matter lectures. So yesterday we saw the motivation of dark matter at different scales, and also the criteria that a viable dark matter candidate has to fulfill. Today we'll continue talking about the thermal universe. And in particular, basics of particle cosmology. Okay. So the basic quantity here will be the distribution function, the partition distribution function, F, which in general is a function of the 3 momentum and the position and time. However, in a isotropic and homogeneous universe, isotropic and homogeneous, this F basically goes, okay, let's go here, will depend on the modulus of the momentum and the time, or if you want, the temperature of the thermal bath, right? We know what the expression in equilibrium, of course, in equilibrium, this guy typically takes this form. So it's Maxwell-Boltzmann, could be Fermi-Dirac, depending on the spin of the species, energy, minus a possible chemical potential, mu, so exponential energy over T, plus or minus 1. So we don't have this factor in the case of Maxwell-Boltzmann. It's plus in the case of fermions, so plus, okay, fermions, Fermi-Dirac, we have the plus, Bose-Einstein, we have the minus, right, it's here. Yeah, in equilibrium. Mu is the chemical potential. It's particularly interesting in the case we have asymmetries. In our case, we'll also basically take the mu to be 0. At some point, we'll take non-vanishing chemical potential. We'll see at some point. An interesting thing is that in equilibrium, this chemical potential could be fixed. For instance, you have an expression, a reaction in equilibrium, A plus B going to C plus D. And this reaction is in equilibrium. You have some relation between the chemical potential of the species. Mu A plus mu B has to be mu C minus mu D. But in general, we'll take all these chemical potentials to be 0, as I told you. So T is the temperature of the bath, right? So we are using the convention where the Boltzmann is 1, K Boltzmann equal to 1. That means that the energy, that the temperature has dimension of mass, has dimension 1. dimension 1, right, energy. Okay, once we have this object, so the partition function, we can define a number of quantities. In particular, we can compute the number density. So a number density will be a function of the temperature. So you have to basically to integrate over the whole phase space. G corresponds to the internal degrees of freedom of the given species, right? So, and we have integrate over all dp in 3 dimensions of f and t, and that's it, right? Of course, in a case of isotropic and homogeneous, this could be rewritten in this form. dp3 And therefore, we can rewrite this in a very convenient way. Right? Where m corresponds to the mass of these species. And so we're just trading the integral on the 3 dimensions to just the integral on over the energy from m to very high energies, right? In principle to infinity. So that corresponds to the number density, right? Number density will come in units of, so it's number of particles over volume. So dimension is mass cube, energy cube. We can do exactly the same for the, okay, this number density. We can do the same now for the energy density. And it's basically the same idea of a function of temperature. Now it's basically the same, putting a factor of energy here. Maybe I should have said that. So here energy, of course. Mass P. Yeah. Can also be rewritten like G over 2 pi square. The exponential E squared, the E. Right? And the other quantity that makes sense to compute is the pressure. Right? So number density, energy density, and pressure is basically the same thing, right? So with we did not write the full expression. P of t same exponential plus minus 1 dE, right? Again, this G is the number of internal degrees of freedom. For instance, well, it depends, right? 2 for the photons, we have the 2 polarization, so transverse polarizations. For gluons is 16. Okay, we have 2 polarizations plus 8 colors, blah, 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 blah. We can do the same for all the particles. And it will be interesting to count exactly the number of degrees of freedom of the standard model. We will take that into account in a minute, right? So we have the full expressions, right? They are not particularly enlightening because, I mean, we have these kind of complicated integrals. However, it makes sense to take some particular limits. For instance, we can take into account the ultra-relativistic limit. So energy much higher than the mass and the chemical potential in general. So for the number density will scale in this way in the ultra-relativistic limit. So it will be basically T cube, right? So this will be so it's T cube, so we'll have will not depend on the mass. It will be strong dependence, power dependence on the temperature. So T cube, number of degrees of freedom, and this funny factor, where this zeta is basically the Riemann zeta function. This guy basically is order 1, right? So zeta of 3 is like 1.2, so it's an order 1 number. So this will depend on the statistics, right? Because we have a plus or minus here. So these correspond to the bosons. In the fermionic case, we have an order 1 factor, which is 3 over 4. 3 over 4, and the same thing. This is 3, yes. For fermions. Yeah. So ultra-relativistic limit, the important thing is it scales like T cube. That's for the number density. For the energy density, again, in the ultra-relativistic limit, more or less. In the ultra-relativistic limit, this takes this shape. So it was pi squared over 30 G star T power 4 is energy density, is energy over volume. So energy, dimension of energy power 4, dimension 4. For the case of bosons, and for the case of fermions, we have a factor 7 over 8. It's not 3 over 4 now, but 7 over 8. Pi squared over 30. Sorry, not G star. G 10 to the 4 for fermions. Yeah, so the statistical factor. Okay, these two correspond to ultra-relativistic limit, right? So no mass dependence, so strong T cube or T4 dependence. And now we can go to the opposite limit, so ultra-relativistic. We can go to the non-relativistic limit. Yeah, where the energy is much smaller than the mass. And in this case, we have the number density yeah, so a power law dependence, 3 over 3/2. And this exponential factor, so this Boltzmann suppression, exponential or minus m over t, right? So when they become non-relativistic, they have this strong suppression, so they basically disappear from the thermal bath. So because they have the exponential of minus mass over t, and the temperature, or if you want the energy, the typical energy is much smaller than the mass. They are non-relativistic. So you expect them to basically disappear from the thermal plasma. So that's for the energy density. For a number density, sorry, the energy density will be basically the mass times the number density. Yeah. So exactly the same suppression. So energy density, I mean, the particle basically disappear. Of course, you expect the energy density to be completely subdominant as well. Subdominant means that they have a strong Boltzmann suppression. And also, the pressure is basically the mass, the number density, sorry. So it's number density times the temperature. And the key point is that this is much smaller than rho. Because compared to rho, you have this factor m over t. I forgot to say a point here. So in the ultra-relativistic case, we found this relation. Of course, I didn't say because I forgot to put the pressure. So sorry, let me go back to ultra-relativistic. So here I put the expression in the ultra-relativistic case for the number density and for the energy density, but we could do exactly the same for the pressure. So the pressure in the ultra-relativistic case is basically 1/3 of the energy density. And with this, so we are always assuming the case that we have a perfect fluid. So with this, we can compute or we can define the equation of state parameter, which is basically the pressure over the energy density. And therefore, this is 1/3 for ultra-relativistic species, for radiation. In the case of, yes, ultra-relativistic. However, in the case of non-relativistic, we have this big hierarchy between the pressure and the energy density. And exactly because we have this, because they are non-relativistic, so the temperature is much smaller than the mass. And in this case, you can also compute the equation of state parameter. And because of this hierarchy, you find that the equation of state is basically 0. Yeah, it's exactly 0 in the case of perfect fluid in the non-relativistic. So you can compute that. I mean, you can do it analytically if you have if you're not going to the dinner, for instance, you can compute all this analytically, numerically, and make compute the evolution of the for instance, the equation of state. So I think it's funny. So I just did this exercise for you guys. So so here, for instance, I'm showing you this plot of the evolution of Rogerio. I'm colorblind. It's super difficult for me to see this spot. So the equation of state parameter, right? So read the pressure. I put dark matter, but forget the dark matter there. So evolution of the omega is the parameter equation of state parameter. So basically the pressure over the energy density as a function of this quantity, which is the mass of the species over the temperature, right? So the time is flowing from left to right. So the universe is expanding, the temperature is dropping. That means that this parameter x is increasing with time. Okay, x equal to 1 is when the temperature of the mass. So basically when the particle becomes, the border between relativistic and non-relativistic. On the left is higher, small x means high temperature. So the particle is relativistic. So the equation of state here, so this blue dotted line corresponds to 1/3. So it's non-relativistic. Very large values of x mean very small temperature, small with respect to the mass. So dark matter is, sorry, not dark matter, the species here, and the species is non-relativistic. So you expect the equation of state to transition to 0. So the only point that I want to show here is that this transition is, of course, it's not instantaneous. It takes some time. So, I mean, of course, when this guy is exactly 0, it's difficult to judge. I mean, there's not a, it asymptotically goes to 0. But, I mean, it is when the temperature is maybe at least 1 order of magnitude, maybe 2 orders of magnitude smaller than the mass. The end. Ah, DM. So yeah, I did this for dark matter, but please forget that. This is any species, so please forget all the DM. Yes, is here at this point is just one species with mass that transitions from relativistic to non-relativistic. Basta. That's it. Yeah, sorry. Yes. Thanks. Yeah, that was the only point I want to raise here. Yeah, questions, comments? Maybe you're super familiar with this, I imagine. Sure.
How is it justified that we chemical potential? Because
Again?
how is it justified that we neglect the effect of the chemical potential?
No, it's not justified yet. You have to take it into account. We are late in that.
Account here.
Yes, in principle, you have. See, I'm always assuming that here the chemical potential is much smaller, and typical. That's typically the case. Okay, let me answer this in different ways. So, in general, you have. Okay. Assuming that this is here I'm always assuming assuming by two okay, is subdominant. You really should do is take it to in the chemical potential. No. No.
I think this one is.
Hello? No, okay, now it works. But now you have a third hand. For instance, in the for dark matter, we have when you have chemical equilibrium, and if dark matter, and if dark matter is there's no asymmetry, the chemical potential are 0. But I will show you some evolution of the chemical potential. Even for the case of WIMPs, so we completely disregard the chemical potential, but we can find the evolution of the chemical potential after the freeze out, the chemical freeze out. Okay. So we can see how it evolves. A la carte. Yes, I can do that. Okay. I have some plots. I can show you. I'm happy to show it next time. So you have an asymmetry, you definitely have to compute the chemical potential, right? Because the chemical potential is what is giving you the asymmetry. Here, I can show that the chemical potential is zero when we discuss, for instance, about WIMs and other mechanisms. In SIMs also, you have to take into account the chemical potential. Yeah, but I agree that's typically disregarded. And there are good reasons to do that. And in particular, if you have symmetric dark matter in this case. Thanks. More questions? Could you, Rogerio, hold me this? No, I'm kidding, no, of course. No, it's fine. Okay, so that was for a single species, right? So we can compare, for instance, energy density for a single species. Thanks, yes. We can ask ourselves, what about the energy density of the whole standard model? So not for a single species, but for this, for the whole plasma. And it's very easy. So what you have to do is to sum over all species. And that's it. So next. No, of course not. So what you have to do, okay, then let me do it this way. This is a temperature-dependent quantity. It's a temperature. And let me be a bit more precise. So we're summing over different species, and all the species could, in principle, have different temperatures. So I'm labeling with I the standard model particles, I in the standard model. So rho I for the species number I with a given temperature. So I let all the temperatures to be different. So this sounds a bit baroque, but actually we have in the standard model different temperatures now. For instance, we expect the standard model neutrinos to be colder than the photons now, at present. So, okay, and this expression, this sum over all the species, I could divide into relativistic and non-relativistic. And it makes sense because they have very different scalings, right? So we saw that for the relativistic particles, the energy density is basically T4, sorry. Whereas for non-relativistic, you have this strong Boltzmann suppression. So actually, this makes sense to compute the energy density of radiation, which I will only take into account the relativistic particles. Why? Because the non-relativistic are very suppressed, they're Boltzmann suppressed. So here, actually, let me write this in this way. So inspired by this, so pi square over 30, G star, I will define what G star by T power 4, right? Which temperature here, for me T, and each time I write T, I have in mind the temperature of photons. So let me put it more explicitly, T gamma, T photons, but I will forget very soon this subindex, right? So what is G star? So G star will count the degrees of freedom of the standard model relativistic that are de facto, okay, and this is a function of the time, that are de facto contributing to the energy density of the universe. And why not all? Because some will be, the non-relativistic will be Boltzmann suppressed. That will not really contribute to that. Okay, so this guy is basically the sum over bosons with mass smaller than T of Gi Ti over T power 4 right? So this kind of weird, this expression, but basically what I'm doing is just summing this. So I'm separating relativistic and non-relativistic. Disregarding the non-relativistic. I'm only focusing on the relativistic. And there's a factor of 7/8 because of the statistics, and that's exactly what I have here. Right? So again, this T is also the T gamma, so T of the photons. And I'm allowing every single species in the standard model to have a different temperatures. This is kind of extravagant because basically all standard model particles have the same temperature because they are in contact, in thermal contact, they are in kinetic equilibrium. So we expect, well, in the early universe, all the standard model particles were exactly the same temperature. However, we'll see the neutrinos, maybe you have seen that before, are slightly colder. So I'm doing all this Baroque thing just because of neutrinos. Yeah? So, and this G star, I have a plot of G star. So here again, please focus on the thick black curve. Now that the lights are off. So the black corresponds to G star, exactly this quantity here. So the number of degrees of freedom contributing to the standard model energy density as a function of the temperature. So the temperature is increasing, so the time goes from right to left, right? High temperatures and small temperatures, right? So here, what you can see is that G star is decreasing with temperature. And why is decreasing? Basically, the temperature decreases, so we have some particles start to disappear from the thermal bath because basically they become Boltzmann suppressed. Here we have this suppression. They are not, the bath is not hot enough to maintain them, so they will for instance, they will decay, they will annihilate away, and then G star is decreasing. What is G star S? Hold on. Yes, so for instance, high temperatures, when the temperature is higher than the top mass, we'll have all the particles to the standard model, and then we can compute this G star, and you guys can do that exercise. So this G star, thank you. So it's like 106.75 when the temperature is much higher than the top mass. Yes. So you start decreasing the temperature, the top will decay into a W and a B, so G star will start decrease, then you have the threshold of the Higgs, W, Z, blah, 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 it will start decreasing. So for instance, so you can see like, I put in I don't know what is that color, like yellowish, second plateau that correspond to the temperatures between, say, MeVs or so. In that case, G star is more like 10 over 10.75, when T is about between, say, 1 MeV and 20 MeVs or so, MeVs. And then it will be 336 when the temperature is between the neutrino mass, whatever it is, and the mass of the electron. So you can compute all these numbers. So here is basically you take into account every single particle in the standard model, and don't forget that there's a factor 7/8 because of the statistics. This 10.75 is when you take into account. So here is I have no room. Here is all standard model particles. Here you have photons, neutrinos, electrons, and positrons. And here is after the decoupling. Here you have basically only gammas and neutrinos. This is when the electrons and positrons annihilate away. Okay? Now, okay, if we have the total energy density of the standard model, basically the total energy density stored in radiation, we can compute the Friedman equation. And compute the Hubble, well, using the Friedman equation, compute the Hubble expansion rate. Yeah. I think we saw that in Kafir's lecture. So Hubble, Friedman equation say that Hubble expansion rate is basically a dot over A. A is the scale factor, the cosmic scale factor. The dot corresponds to derivative with respect to time. And this Hubble expansion rate can also be written as the square root of the total energy density in the universe over 3 times m Planck square. M Planck is the reduced Planck mass, which is basically 2.4 10 to the 18 GeV. So it's really a number. And here you have to put everything, right? All energy density. You have to put cosmological constant, curvature, relativistic particles, non-relativistic particles. So all the energy density in the bath. So we know what the expression of the energy density of the standard model, somewhere here, right? So in the early universe, so the universe is flat, we don't have a curvature. In this epoch, so we were talking about, we don't have the cosmological constant is not giving an important contribution. So this will be something like pi over 3, G star over 10, G star, that depends on the temperature, T squared over the Planck mass. Yeah. Okay. Fine. That was the standard model entropy energy density. The Hubble rate. Hubble rate assuming, so that's important to say, I forgot, sorry. For let me put it there. Radiation, standard model radiation dominated universe. Yeah, and that's what you're assuming, right? So you're assuming that this rho, the energy density in the universe is dominated by standard model radiation. Okay? Hubble made, and of course, Hubble will scale different ways depending what's the dominant component of the universe. Yeah. Okay. Another key point is the entropy. Okay, so the point here that during most of the evolution of the universe, the universe was adiabatic, to have a adiabatic evolution. It's not always the case. So for sure, there were periods in the universe where the evolution was not adiabatic. For instance, during reheating, right? So remember, reheating is a transition between a universe dominated by inflaton, so right after inflation. We have to transition from that to the domination of the inflaton to a domination of standard model radiation. So you can imagine, so the standard picture, the inflaton the inflaton decays into standard model states. So in that, during reheating, you don't expect, for sure, the entropy is not conserved because it's not an adiabatic process, right? Of the standard, of standard model. Yeah. However, let's assume that well after reheating, we have or at least in the standard cosmological scenario, all the processes are adiabatic. So standard mode entropy is conserved. So standard mode entropy is S, capital S. S is conserved. So adiabatic process. Yeah. So if you know the entropy, the total entropy, so capital S, we can define the entropy density. S, small s, that's an S, is basically the total entropy over the volume. The volume is a cube, right? A is the scale factor, 3 dimensions, a cube. And we can compute exactly what the expression for the entropy density is pure thermodynamics. That can be done. I don't think if you guys are interested, it takes some, yeah. It's pure thermodynamics. If you want, I can do it next week, tomorrow, or in the Q&A. But you can also find it in the Kolban-Turner, so it's kind of standard computation. So this entropy density, you can write it as a function of the pressure and the energy density over T. And for you have an extra factor if you want, so you can have minus chemical potential times number density. Okay. But we will disregard it. Okay, it's there. Yeah. So we can also, so we have the entropy density that depends here, pressure and energy density. And again, remember that in the non-relativistic case, both the pressure and the energy density are Boltzmann suppressed, so are very subdominant with respect to the relativistic particles. So these guys, so the entropy density will be by far dominated by relativistic species. And then if I plug this expression in the ultra-relativistic limit for the pressure and energy density, I can rewrite the entropy density, as a function of temperature, like this. Two pi squared over 45, G star S, and T cube. T cube before it was T4. Now it's T cube because, yeah, basically it's T4 over T. And G star S is defined in a very similar way as G star S, as G star. So it's basically the same thing. Huh? So I'm summing over all species in the standard model, both relativistic and non-relativistic. It's dominated by the relativistic species. And I have two terms because I have different statistics, right? Different statistics. So this G star S of T is, again, the sum over bosons with mass smaller than T, Gi, Ti over T, power 3. And again, here, again, I'm referring to temperature of the photons, right? This is my reference. Yeah. Here is always photons, plus the sum fermions with mass smaller than T, so those are relativistic, Gi, Ti over T, power 3. And and that's the G star, you can see there, right? So G and G stars are basically, so G star, okay, G star is the black line, G star S, so the one contributing to the entropy is the dashed blue lines. So basically the same, right? So a high temperature, actually when the temperature is higher than basically the mass of the electron, they're exactly the same. Not similar, but exactly the same. However, something happened when the temperature is of the order of the mass of the electron. We'll see in a moment. And we have a small difference. So I'm making a big deal out of this. However, for our purposes, G star is basically the same as G star S, because we're focusing on higher temperatures, and you can see that it's exactly the same. But I think it's important to take into account that these guys are different. Questions, comments? So let's exploit a little bit S, what the conservation of the entropy. So if entropy is conserved, so let me put S is equal to small s, so entropy density times A cubed, which is more or less G star S T cubed A cubed, and this is constant. It's an arrow. That means that the temperature scales like 1 over G star S 1/3, 1 over A. So you have a scaling of the temperature as a function of the scale factor. So the universe expands, the temperature drops. Right? It's not. Yes. Thanks. Good. Thanks. So that's important. I mean, it's very clean, right? It comes from the conservation of entropy. So assuming that the processes are adiabatic. So again, when the processes are non-adiabatic, for instance, during reheating, you don't expect this kind of scaling, right? Good. One more thing. Where is it? Here. Erase this part. So let me go a bit deeper into this plot and see why we have a small difference between G star and G. So let's remember the evolution of the universe. So when the temperature of the universe is around, or was around, temperature of the photons, like right, 1 MeV, in the MeV scale, the standard model neutrinos decouple. What does that mean that they decouple? That these interactions, so for instance, annihilation into E plus E minus, and elastic scattering with electrons and positrons. So both inelastic and elastic scatterings are not in equilibrium anymore, right? So they are not in equilibrium. Let me put it like this. So that means that we have like this this plasma of neutrinos and of electrons and photons that they don't talk anymore. So they are there, they're contributing to the expansion of the universe, but they are not in thermal contact anymore, right? That's it. And then when the temperature drops a bit more, and it's sort of the order of the mass of the electrons, what happens? The electrons annihilate away, basically into photons, right? That means that they are injecting entropy into photons, right? However, not into neutrinos. And neutrinos are not in thermal contact with photons. So that means that you will kind of slightly reheat the photons with respect to neutrinos. And you can compute that knowing that the entropy is conserved. So this kind of reheating. So this, in principle, increase of temperature, however, it's never an increase, it just decreases slowly, of the temperature of the photons with respect to the temperatures of neutrinos. You can compute it assuming the annihilation is instantaneous and using this expression. Oops, something happened here. So it will be dictated by the change of the number of degrees of freedom, G star S, in the case where you have photons and electrons, compared to the case where you only have photons, over 1/3, right? And that you can count the relativistic degrees of freedom that when you take into account both photons and electrons and positrons, and when you only have photons, and this is like 1/4. Only consider the degrees of freedom. Okay? And we know that now from the CMB, the temperature, let me put of photons, is around 2.73 Kelvin. So this is the CMB. And that means that the temperature of the neutrinos using this factor, 11/4 over 1/3, is around 1.95 Kelvin. Just say mu B, the cosmic neutrino background. That has not been detected, but we, in principle, I mean, there are some experiments that aim at detecting the CNU B, for instance, Ptolemy. Yeah? So, and that's exactly what you see there. So, so this small difference between G star and G star S at low temperature, so the temperature is smaller than the mass of the electron, is due exactly to this friend here, right? Because you see that there are different scalings. Here is T cube, and there is T4. Yeah, so I'm not very fast today. So I can compute, now I can compute, for instance, this number here that I didn't compute. So I can compute that. So let me see how I compute that. So G star will have contribution of the photons, so 2 degrees of freedom, 2 polarizations. We also have a 7/8 because of the statistics, and we have neutrinos. So here we have photons and neutrinos. We have 3 species, 2 spins, and the factor 4/11. Oops, over 11, power 4/3. And this is exactly 336. And we can do the same exercise here with G star S. Let me compute it, G star S. When you have photons and neutrinos, and it's exactly the same. Huh? So we have a 2 coming for the photons, 7/8 statistics, and we have neutrinos, 3 times 2, 3 generations, 2 spins, 4/11, and now it's 3/3. So basically 1. And this is 391. Yeah. Good? Questions? Yes. Yes, sorry, I'm abusing the language. Was here. So what happened, okay, after the decoupling of neutrinos, we have like the standard, if you want the standard model, okay, not the standard model. We have a plasma of electrons and photons, and we have neutrinos as well. But they decouple, they didn't talk at all to each other. So at some point, electrons annihilate away, right? They will transfer its energy, or entropy if you want, to photons, but not to neutrinos. Right? So we are producing more photons, so you can see that if the temperature is raising. It's raising with respect to the one of neutrinos. It's never raising in cosmic scale, just that it's cooling down slower. Yeah? So each time you have this threshold, sometimes people say this reheating, but it's not cosmic reheating after inflation. Yeah. And it never reheats in a sense, it never increases the temperature. It's just that it cools down slower. I may have a plot, something here. Okay, yes. This is related to your question, Nico. So here again is the effective equation of state, not again. Here's the equation of states of the universe, W, thanks, as a function of the temperature. So temperature is going, so it's increasing, 10 to the minus 6, 10 to the 4. So it's exactly the same axis. Huh? So time is flowing from right to left. So this is the effective equation of state of the whole universe. You expect it, it's radiation domination. You expect it to be 1/3. So this dotted line is 1/3, right? However, you can see that there are deviations from 1/3. So the universe is basically, and this range of temperature is dominated by radiation. So you expect the equation of state to be exactly 1/3. However, each time you cross a kinematical threshold, so particles become non-relativistic, so they have an impact. So you have, they become non-relativistic, but they are not still super Boltzmann suppressed. So you expect the total, or the effective equation of state to slightly decrease. So you have a small decrease, right? So it never reaches 0, so it's never matter dominated. However, it's not exactly 1/3. Yeah? So each time you have this, you cross this threshold, so each time you decrease the number of degrees of freedom, you have a small decrease on the equation of state. So that's what I call reheating. So the universe is not behaving, it's not scaling exactly as radiation. Very close, yes, indeed, but not exactly. Yeah? Fine, questions, comments? Okay, now, the Boltzmann equation. So I have a slide for that. No, I don't. No, wait. So the Boltzmann equation is very easy. So I will write it for you. The most general one. That's it. So next. So the Boltzmann equation is basically this. So we have the Liouville operator and the collision operator that are function of, that depends on the partition function, f, it's not here anymore. So it's in principle as easy as this. So L is the Liouville operator. And it's basically a time derivative. So the information encoded in the Liouville operator is the change in time of the phase space density, so the partition function. So I will not write it here, but it's think as a time derivative. C is the collision operator. And it encodes the information of the change of the number of particles, right, per unit time. So here the Liouville operator will encode basically the cosmology, yes, the expansion of the universe. right? Whereas all the particle physics will be encoded here in the right-hand side in the collision operator, right? So Cosmo and particle physics. It's possible to compute the Liouville operator, and I can do it for you. It's kind of long and kind of painful. It's painful. However, several things. So here really depends. Okay, that's in principle what you want to solve. You want to solve the evolution of the partition function. However, typically for dark matter that is not required. You can do in moments, sorry. For instance, the first moment is the number density. This is what we had here. So the number density will be the solution. The first moment of the Boltzmann equation is the evolution of the number density. The second will be basically the energy density. So in general, this equation, even the simplest cases, is a pain. It's very complicated to solve, analytical, but even numerically. I think analytically it's just not possible. Huh? So what we will do is to focus on the first moment, which is the evolution of the number density, the dark matter number density, right? So this will simplify our life and by far. Okay, so even if we take into account, you focus on the first moment, so the evolution of the number density is not super simple. That could be the Liouville operator can be computed, and also the collision operator. So this could be done, and it's very clean. However, it will take time. Again, I can, if you insist, I can do that next week or tomorrow, or in the Q&A. However, I just want to give you like the basic idea for you to have a taste of how this appears. So let's first study the Liouville operator. Yeah. And actually what we want to do is we want to compute the evolution of the number density. So the evolution, remember, n is the number density, t is the time, so the time evolution of the number density. So the number density is basically the number of particles over the volume. Look, easy. And I can make the derivative of this sentence. So the number of particles, so at the n will change the number density if you have reactions that change the number of particles, so number changing interactions, or if the volume changes. So the volume, we know, it will increase, so they will have a negative contribution. This will be minus a negative contribution due to the Hubble expansion, and plus or minus, I don't know, maybe plus, number changing interactions. Right? So that's how we can go from here to here. Easy. Now, Hubble expansion. Here, better. We know that by construction, n goes like 1 over a cube. Number of particles over the volume, n is like 1 over a cube. That means that if we make the time derivative of this quantity, n times a cube, this is 0, right? If there are no, okay, let's assume there are no interactions for now. No number changing interactions. Number changing interactions. So this friend here is 0. And let me just compute this. I mean, chain rule, dn dt times a cube, 3a squared n dA dt. Nothing fancy. And remember, the Hubble is nothing but a dot over a, right? So I can rewrite this as a cube dn dt plus 3hn equal to 0. Yeah? That means that this friend here is 0. And here's exactly what we want, right? So we're having, so we can rewrite this as the ndt minus 3hn plus this parenthesis here. So this is exactly the term that that dilutes the dark matter or this species because of the expansion of the universe. Remember, h is the Hubble expansion rate, right? And this 3 is very important. This 3 means that we have three dimensions, spatial dimensions. So it's negative because the universe is expanding and is decreasing, three dimensions. Hubble is the expansion rate, Hubble expansion rate, and it's proportional to the number of particles. Yeah. So that, of course, is not a completely very schematical schematical way of finding the Boltzmann equation. This could be done, I mean, in a very good mathematical sense. We will not do it here, but you can take a look. Okay, that was for the Hubble expansion. Now, what about the collision term? So the collision term with a single S, no? Well, 1 or 2. So here we'll assume these 2-to-2 interactions. So X could be chi, the dark matter, plus B goes to C plus D. So 2-to-2 interactions. And we have one species that we want to keep track. So N will be the number density of chi, right? The dark matter or whatever. At this point, we don't care about the nature of chi. So the collision term will be, sorry, let me go back here. Are you ready? No, sorry. The n dt, we say that is, let me put it this way, plus 3hn. And the collision term will be basically a sum over all these processes that change the number, the number of chi particles of this reaction, chi B into CD, summing over B, C, and D. Very schematical way. Yeah? And now let me write this guy. Something in this way. So 2 pi power 4. So the delta in 4 dimensions that encoded the conservation of momentum and energy. Yes. The times the Lorentz invariant phase space. Right? This d pi corresponds to the, I will write it, well, I can do it now. I'm not done, huh? times the amplitude square for the process, chi b into cd, times the partition function, chi b. Yeah. So delta in 4 dimensions, conservation of energy and momentum, the phase space for each particle, the amplitude square, and the partition function for all the particles in both initial and final states. So these guys, the pi, are just I can write it for a species I. Lorentz invariant phase space. Yeah. And this f, so this partition function in principle could be very complicated. However, we assume that at least these guys are in kinetic equilibrium. So they assume first that they're in equilibrium, so we have a temperature defined, and we also assume that all the temperatures are the same. So that this reaction brings the system in kinetic equilibrium, meaning that all the particles will have a temperature, and the temperature will be exactly the same. That's the assumption that we are doing. And also that we will forget the statistical factors, so we'll take the Maxwell-Boltzmann. Yeah? So that means under all these assumptions, this F will be basically F at, okay, let me put it at temperature. Okay, no. F at equilibrium. And yeah. So they will share the same temperature, however, they don't have to have exactly the equilibrium abundance. But well, at least the shape is the same. So this is giving me the shape. This is giving me is like an overall factor. So I have the partition function. It will have a shift, vertical shape. So we can have more or less particles that expected from equilibrium. So this is assuming kinetic equilibrium. Kinetic equilibrium plus Maxwell-Boltzmann statistics. And that allows me to rewrite the Boltzmann equation here. The NDT plus 3HN minus we have room. Continue here. And, okay, and here is chi. We are tracking the evolution of chi. In principle, we have to have a Boltzmann equation for every single species. So here we only care about chi, so we have a Boltzmann equation for chi. So the evolution of chi comes from the Hubble expansion rate. And here the collision term has this sigma v, which is this sigma v is a thermally average annihilation cross-section or production cross-section. Right? And chi and B and C and RD correspond to number densities of the species, and this label equilibrium corresponds to the distribution in equilibrium. So Maxwell-Boltzmann, Fermi-Dirac, Boyce, Einstein. So I haven't defined this sigma V. So this in these brackets, as I told you, it's a thermally average annihilation cross-section, and it really makes sense. Okay, this depends on the temperature. So it makes sense, right? So if you look at the way how the collision operator is defined, you can basically see that this is basically a cross-section, right? It's a cross-section with this funny guy. So we don't have here really a cross-section, but you have thermal average, and it kind of makes sense. Remember, a cross-section depends on the energy density of center of mass energy, so the S parameter, Mandelstam parameter, energy density, the center of mass energy, cross-section depends on center of mass energy. Here we have a thermal bath. So all particles have like crazy velocities, crazy energies, okay, defined by their distribution. Here, so it makes sense to think about the cross-sections or the interaction rate that depends not on the center of mass energy, but the temperature. That's why this guy depends on the temperature. We're really averaging over the distribution of energies of these guys. Yeah, we have like a few minutes more, no? Okay, that's in general. Now let's go. Okay, questions, comments? So there's a particular interest scenario. So the Lee-Weinberg scenario, 1977. So it's just a specific case of this scenario. So what you have is not chi B into CD, but really two chi's, so annihilation of two chi's, which will be the dark matter, into two particular particles, which are any standard model particle. So it's annihilation of chi, who are our dark matter candidates, into two particles of the standard model that in the thermal bath. That's important. So if these guys are in the thermal bath, this expression, this Boltzmann equation, could be simplified. So it will be simply the n of the n chi, right? dt plus 3h n chi equal to minus sigma v. So n chi square. Let me forget this label chi. Yeah, I'll put where? Here. N is equal to n chi. And basta. Minus n square minus n equilibrium square. Just this here. C and D are in equilibrium, so this becomes 1, and this is n chi equilibrium, and B is chi as well, so n chi equilibrium square. Where this sigma V, in general, is the sum over all possible final states. So chi into II. And I is all the standard model particles that are present in the annihilations, right? So we are summing over all the possible final states. Okay, so in principle, that's what there are several cases where this Boltzmann equation is the object that we want to solve. It will give us the evolution of the dark matter number density. However, okay, and you guys are super invited to play with this equation, for instance, numerically. At this point, you can try to solve this numerically. You have all the ingredients. you have, if you assume that the universe is dominated by standard model radiation, you have exactly the shape of H, so it's T squared over the Planck mass. This guy, you don't know. Of course, it really depends on the particle physics model that you have in mind. You can, as a first approximation, take this as a number, and you can see what is the number required in order to reproduce the observations. And an equilibrium, you also have it, right? Is the, we have seen, depends on the statistic. If it's non-relativistic, as you want that one to be produced when it's non-relativistic, this is just the expression that we saw. In general, I mean, if it's a Maxwell-Boltzmann, you can use the Bessel function. It's a Bessel function of the second order, but you can also use the exponential that we discussed previously. However, there's a problem is that this expression, even if the equation that you want to solve, is kind of, I mean, it's not very useful. And it's not very useful for several reasons, because here, for instance, you're tracking the evolution, the time evolution, right? However, this quantity does, I mean, I don't know what the dependence on this with time. So this guy naturally depends on the temperature, right? And Hubble as well. And here you're constructing this as a function of time. So it's not clear how to do that. So what we have to do is to make some change of variables and assume some relations between the time and temperature. So until here is very clean, I think, the derivation. Of course, we have done some assumptions that may not work in all the cases. But if you want to really work with this, you have to make some assumption about the evolution, about further structure of Hubble, who's dominating the energy density of the universe, so how Hubble is scaling. So that's one piece of information. But also how, okay, so Hubble, but also how the temperature is scaling. So there are two important ingredients that have to be taken into account. And if I still have a couple of minutes, no? 8. So, okay. In the next 15 minutes, I will discuss this. Perfect. You already closed my mic, right? So I will just do. It's a stupid change of variable, right? But I will do it in all the details, because I would just want to be you aware of the assumptions that we are doing. But what I will do in these 7 minutes and a half is really a change of variables, nothing else. Where is it? Okay, here. So we will assume two things: conservation of the standard model entropy, meaning adiabatic process. Yeah. So it's exactly what we did here. So the standard model entropy is conserved. S is standard model density times A cube. It's a constant. Right? So I can compute the S over the T, and it is 0. Surprise, surprise. And let me do it in all the details. A cube ds dt plus 3a squared s dA dt, and this is a cube ds dt plus 3hs. Nothing, I'm not doing anything fancy. Right? So this bracket here is exactly 0. And that allows me forgot to say that the change of variable that I want to do is I want to use this dimensionless variable. Let me put it here. Y, I will define Y as n over S. So number density over entropy density. And X, which is the same that you saw before, is the mass over T. Yeah? And making this change of variable in principle make completely sense. And why? Because this, so S goes like T cubed, right? S goes like T cubed. N goes like 1 over A cubed. And the entropy is conserved. A cubed goes like 1 over T. So these guys scale like T cubed over T cubed. So is 1. However, so this completely makes sense. It's a covariant, so not covariant, co-moving volume, quantity that means that it grows with the scale like the expansion of the universe. So it really makes sense to define this kind of objects in the case where the standard model entropy is conserved. So in the case where you can guarantee that T goes like 1 over A. However, in general, this is a very bad idea. Huh? But however, he will use this object, and we'll come back to these points where it makes sense to define this kind of object and not. So you be careful. So these are the guys that we want to use. So instead of n number density and time, we'll go to y. So the co-moving number density and x, which is basically a proxy of time, 1 over the standard model temperature. So now, let's take this piece here. So the n over dt plus 3hn. I will just replace n here. So it really, what I'm doing is really a change of variable. This is equal to y ds over dt plus s dy dt plus 3hn. And I'm doing this because here I recognize that this piece here is 0. Yeah. N is y times s. So I get the s dt plus 3hs times y. So I factorize out the y. So these two fellows are 0. So this guy is just s dy over dt. So first thing, conservation of standard model entropy. Second assumption that we are doing is a radiation-dominated universe. Standard model radiation, to be more clear, to be more specific, radiation domination. And the universe is dominated by standard model radiation. Hubble, we saw what it was, pi over 3, g star over 10, t squared over Planck mass. From the Friedmann equation that we know that A, the scale factor, goes like the square root of time. And therefore, times goes like 1 over 2h. Maybe Kafir discussed this, I hope. So I just want to complete the change of variables. So that means that dt, so the derivative of time with respect to the temperature is basically minus x. X is this friend here over h times the mass. And I also will use this fact and this fact that the derivative with respect to time, I will write it in this way. So I can always do this, dt time yes. t dx. Just a change of variable, that's the only thing I'm doing. And I know all these pieces, and this is basically h times m dx. So again, I'm rewriting this equation, assuming conservation of standard model entropy and standard model radiation domination. And this allows me, in the last 2 seconds, to rewrite that equation, this one, in this way. dy dx everything in terms of these dimensionless quantities, y, the co-moving number density, and x, the inverse of temperature. So sigma v, standard model entropy, x and h, y squared and y equilibrium squared. So y equilibrium is basically n equilibrium over S. And that's it. I think that it's a good moment to stop. Just do one thing more. So I encourage you guys to try to play with this equation. So you have all the ingredients, and you can just solve it numerically. Putting here some numbers. So you just assume a mass equal something, any number you put here, and the exercise is what is the sigma v? It's a number. At this point, take this as a number. And what is the number required in order to reproduce the whole observer, the dark matter abundance? Some homework for tomorrow. And yeah, so let me stop at this point. Thank you.
Just a quick question. I think that I missed a little the behind the definition of that variables, y and the x.
Yes. Yes. Okay, you could in principle keep track of n. However, n will change because of the expansion of the universe. So you would like to find and to define a variable which is which already contains that information. So in general, this is not a good idea. The best idea in general is to define a variable, because what you know is that there's no interactions. N goes like 1 over the volume, a cube, right? So what you really want to define, say a capital N, which is n times a cube. This always works, right? It always encodes or contains the expansion of the universe. However, from here you're having an extra assumption. You're assuming that you have only adiabatic processes, that the entropy is conserved, and therefore A goes like 1 over T. Yes? If A goes like 1 over T, instead of having N, not A cube, but yes? And this is basically N over S. Yeah? So the idea is that if you don't have interactions, suppose there's no interactions, if you keep track of N, you will have that N goes like 1 over A cube, so it's diluted. However, if you study these objects, it will be constant, because it's already contained here. So this will work if the entropy is conserved. You can define object and it will be constant. Yeah. And y x, so not time. So it makes sense to have dimensionless objects. Okay, yt downstairs and not upstairs. I don't know. We have the evolution from left to right, so 1 over the temperature is more natural. But I have a better explanation. But it's just a choice, huh? Yeah. Several questions, but what? No, it's not. For instance, if you want, you can do, if you do baryogenesis or leptogenesis, you can exactly use the same methods, and they're used. Of course, in baryogenesis, you have to take, well, maybe the big difference, you really have well, there's an asymmetry, right? So you really want to keep track of the asymmetry, so you have to take, be very careful with the chemical potential that I'm here disregarding. Yes, that's the short question. Yeah, you can do the same exercise for photons, however, you don't need to, because they are in equilibrium, so but you do it. But you know already the answer, so the distribution of the equilibrium density at the temperature of the photon, so CMB now. Exactly. So you do it, but it's super boring. No need to use this machinery too. Yes.
Okay, let's thank Nicolás again and come back.